presentations. We'll have some Q&A at the end. We want to take a moment to thank our sponsors, to Chelsea and Chapman in general. Thank you for letting us host these monthly events here. This entire facility is brand new. It's beautiful. If you're interested at all in pursuing a master's program, and you could have someone like Chelsea as a professor, I definitely recommend you take a look at the school. The MS in Electrical Engineering and Computer Science program, they've been doing some awesome work and research. And if you're interested, you can feel free to contact Hillary Anderson. She was here last time, spring break. So either Hillary or Chelsea, or if you want to reach out to us, we could point you in the right place too. We do a lot of events with the UCI Paul Mirage School of Business. So Pablo and I actually met there in 2018. They have a business analytics program. At the time, UCI didn't have a Master of Data Science program, which they now also have. It's at a different school altogether, but we still do some events with them. Our biggest event of the year is actually coming up soon. It's the weekend of April 27th and 28th. We host an annual hackathon. It's been at UC Irvine now for about 7 years or so. It's a really fun time. It keeps growing a little bit every year. Last year we had about 80 participants. Tons of fun. And there will be food, there will be mentors. And the idea is you can come as a team and try and tackle the hackathon problem together as a team, or if you want to show up solo, we'll help place you into a team with either partial teams or other groups of individuals, but it's a lot of fun. We usually start the day on Saturday with like a morning training, so anyone's welcome to come and sit through those training workshops. We're still sort of refining what those trainings are going to look like, but I think there will be an Arrow and DuckDB training because we might be dealing with a bigger data set. Generally speaking, you can't ingest a data frame or a data set into your memory, so into your Python environment or your R environment, if the size of that data set exceeds your system's available RAM. And tools or platforms like Arrow and DuckDB actually allow you to process larger than RAM data sets, which is really exciting because now all of a sudden you could only have a MacBook Air that has like 8 gigs of RAM, but you can process 100 gigabyte data frame and really fast. So really fun stuff working with big data. We also have this one is still in flux, but there is most likely going to be in May a panel discussion at UC Irvine's the College of Computing, also open to the public, and this will be a panel discussion most likely on generative AI. Sorry, lots of ifs and potentials, but that should be mid-May, I think May 15th, or right around there. So yeah, without further ado, we're here to listen to Travis talk about G-Thangs, Causal Inference with R. G-Thangs. G-Thangs. A little bit about our professor. So Travis Gerke, SCD, is a Director of Data Science at PCCTC, a contract research organization that facilitates clinical trials and real-world evidence studies in oncology. He's the founder of C-Structure, a company that provides a collaborative platform for causal design and inference, and he's constantly putting out amazing materials on the web for open source development and causal inference and R. So yeah, without further ado.
Thank you for having me.
And would you like questions?
Yeah, you can interrupt me.
I'm for the end?
I'm super chill about pretty much everything. So interrupt me or eat, get up and do things. It doesn't matter. So anyway, yeah, this is my wife thinks that I'm like ridiculous for making jokes like this, so I apologize if I'm not that funny. So thanks for the introduction. I mean, generally for me, yeah, that's me. I'm Travis. I trained originally in biostats and epidemiology at Harvard. Then I was faculty at University of Florida, later at Monte Cancer Center. I got tired of the tenure track thing and not being able to pay off my student loans, so I left and went to industry. My first industry job was like in the hospital arm of Monte Cancer Center, which was cool. I was working on some health informatics tooling, like AWS, how do we do data science in the cloud instead of on-prem. Kind of they were on the precipice of doing some really cool stuff there, so that was fun. Now, yeah, of course, I'm at the PCCTC. We run clinical trials, academic trials. We do a few kind of industry type trials too, so that's always fun. I have other things going on too, because I just don't know how to turn it off. I'm the co-founder of the C-Structure thing. You'll see some examples of what that software does in this talk, actually. But I'll keep this talk more about R and not so much about that, but it's fun. And then I'm involved with this Toby Health company. It's doing urine-based diagnostics for all kinds of different diseases, and it's going to be cool. That's a reference to Sherlock Holmes' dog, if there are any geeks like that in here. In real life, I lived in Florida for a long time. I didn't go to school for a long time either. I was in working construction. I'm an HVAC technician, so I worked on air conditioners for a long time in Florida. Then Florida got weird, so we left. And we lived in an RV, like traveling the country for a couple of years. I have 2 boys. I coached the baseball team. That's how I spent most of my spare time. That was our RV. That was in Big Bend, Texas, a few years ago. Yeah, now I live in San Diego, North County, so it was only an hour and a half to get here. Yeah, good to meet you all. Okay, suppose we're in Disney World. This is a ride at Disney World. It's called the Seven Dwarfs Mine Train, I think it's called. It's got an F instead of a V, which I like really bugs me. But was the movie like that too? Is it the Seven Dwarfs? Snow White and the Seven Dwarfs? Dwarfs. It's weird. I don't know, but it's a really popular ride, and lines are long. So 8 a.m. Around when Disney opens, you might see something like this, 65 minutes already at the Seven Dwarfs ride, which is actually pretty good because often these waits are like a lot longer than an hour. And so you might ask yourself, well, if we are Disney and we're running this thing, we can actually make that number anything we want. And we could think about like what different kinds of impacts of giving different estimated wait times, maybe these posted times. So if it said like 65 minutes at 8, an hour later at 9, the line might look like this, like super long, because everyone's like, oh, it's only 65 minutes, let's all run across the park and go to Seven Dwarfs mine train. And instead, if at 8 a.m. it said it was 180 minutes, what might happen is something like this, where like an hour later, everyone's like, forget that, I'm gonna go listen to Small World for a while, and there'd be no line here at all. So we're obviously setting up an intervention type causal question. What would be the effect, the causal effect of intervening upon this exposure, we'll call it in this case, which is the posted wait time for the Seven Dwarfs Mine train at 8 a.m. And we want to know what the effect of doing that would be on the length of the line or the wait time at 9 a.m., the actual wait time at 9 a.m. So that's kind of what we're setting up. And so this is the causal question now. So this isn't like a prediction question. It isn't like, do posted wait times at 8 a.m. predict what the wait time is at 9 a.m.? It's an intervention style question, a causal question, like what if we do this thing, what will happen next? So can we strategically set wait times, if we're working for Disney or doing a Disney thing, such that actual wait times at 9 optimize maybe attendee experience? Maybe we could think about like trying to triage the line lengths and wait times in a way that they're kind of in a steady state throughout the day by just manipulating the posted wait time. And then the actual wait times might kind of remain somewhere at a tolerable level. Okay, so the ideal way to do this would be to set up a randomized controlled trial. If you're in the health space, you'll know that well. Or if you're in business or other space, the same thing, A/B test, same idea. So the way we could work this for this particular example is every morning at like 7, let's flip a coin. And if it's heads, let's post a wait time at 8 a.m. at 60 minutes. And then we'll measure the wait time at 9 a.m. of what the actual wait time was. And if it's tails, then we'll set the posted time at 30 minutes instead of 60 minutes, and then we'll measure what the wait time was at 9 a.m. Okay, so what's happened now is I've set up, this is the first DAG we're going to see. So these are causal diagrams. DAG stands for directed acyclic graph. So they're acyclic because you can't, like, one thing can't cause itself over and over again, for example, so there's no cycles. And each node is like a variable or an intervention, and then each arrow represents a cause, so like one thing causing the next thing. And these things are always time-ordered. You can't like have things in the future causing things in the past. So this represents that A/B test maybe that we just set up, where coin flip is going to cause the posted wait time and nothing else. There's no other causes of the posted wait time. It doesn't have to do with like what day it is or like season or anything. It's just a coin flip. And then we want to know what is the strength or what is the nature of this causal arrow from posted wait time to the actual wait time. Is it 0? Is it like positive? Is it negative? If we post 60 minutes instead of 30 minutes, we're going to see a shorter wait time at 9 a.m. That's the causal effect we want to estimate. And what I will propose now is that when we do this way, the correlation between the posted and the actual wait time is causation. So this is the thing that every stats class you ever took told you not to believe. Correlation is not causation. That's true until it is. So if you have an actual causal effect of something, there will be a correlation there. And if you designed the trial or the study well enough, that correlation that you estimate is in fact the causal estimate. That's the way randomized controlled trials in medicine work. You set it up and you just randomize 2 groups of people with a coin flip or some random number generator or whatever, and they both get like drug A and drug B. Nobody knows anything else. The only thing that could cause a difference in the outcomes in those 2 equal groups of people would be the drug, whether they got drug A or drug B. So that correlation ends up being a causation. That's just true. Do you believe?
Is that like,
Yes.
Yep.
that's like ideal, right? Like that's supposed to be the case, but then there's always like room for, right?
Yes.
People
So that
fail
there's a whole layer of
genetics.
assumptions that the RCT got ran well, that the A/B test went well, like stuff could have messed up. Who knows? Like the ride broke down. Who knows? Right? Yes, you're totally right. In the real world, like this doesn't happen, which is why I'm calling it the ideal. And in fact, we can't do that here at Disney in our hypothetical example, because we'd probably be setting up really crappy customer experience over this like coin flipping test that we're going to do. Because what if like the ramification of 30 minutes versus 60 minutes, one of those was like really, really bad, and then everyone started having a terrible time, but we'd be going as a data science, I don't know, we got an A/B test going, we have to keep flipping the coin and doing the thing that everybody hates. Can't do it, like, right? And that's the way randomized controlled trials can fall over in the real world too. Either people can't adhere to the drug because it's intolerable, or like something, like who knows what happens, or other things like lung cancer, like smoking and lung cancer. We can't design a randomized controlled trial for that for obvious reasons, ethical reasons, health reasons. But we want to somehow still back into some causal knowledge about that process. So that's where we're headed now. So that's maybe the data we have is not the ideal data of the A/B test of the randomized controlled trial. Touring Plans is a website that helps people that go to Disney or Universal theme parks plan their day. And their main value add to people is that they measure like posted wait times and actual wait times all day long, every day. And you can like become a member of this thing, and you can like really hack your Disney experience by like using they have like an API. It's really fancy stuff. We're fortunate that Lucy D'Agostino McGowan, who I'll mention a couple times later because we're writing a book on causal inference and R together, she has friends at Turing Plans, and they like figured out how to get some data that's public and put it together. And it's now an R package called the Turing Plans R package.
That's so cool.
And it's just a data set, and it has like data from 2018 to 2019. I don't know, but anyway, it's got a whole bunch. It's a pretty big data set. It's fun to use for like lots of reasons. We're going to use it here to explore that causal question I just set up. But if you're ever looking for like data to toy around with, this package could be good for you. So this is the data we have. None of this came from like randomized A/B trials or anything like that. It's just like what Turing Plans like observe. They send people through the lines, or they're tracking people on their phones because they're logged into the thing, and they see how long they wait in line, and they like kind of refine their models from there. They measure it all. Okay, so the observational study that we can do is not the randomized study that we wanted to do, not the A/B trial, but we're gonna just go with what we got. And what's gonna happen when we have any observational study in general is we're gonna have to deal with confounders. And the important definition of a confounder is it is a common cause of exposure and outcome. You've probably heard other definitions of confounders somewhere along the lines in your life, and I will claim that those are not the right ones. This is the only right one. So you've heard things like a confounder is something that predicts both the exposure and the outcome, or like if you remove it, it changes the effect size by more than 10%, or there's all kinds of weird rules of thumb. In the causal inference world, this is the definition. It has to be a common cause of the exposure and the outcome. So I've drawn a really simple example here where extra magic morning so what extra magic mornings are is this thing that Disney does where people that are staying at a Disney resort get to enter the park like an hour early because it's a perk of like staying at a Disney resort. And so you get these extra magic mornings, and they run them. It's not every day, and you never know which park it's going to be at. Like, so it's like some like cool thing, I guess. Lucy gets really revved up about this because she loves Disney. I'm doing my best. There's like, so these extra magic mornings that may or may not happen at Disney, which is where the Seven Dwarfs train ride is. Like, so this now you could imagine if they have one there, or if they don't have one there, it's going to cause a difference in the posted wait time. Because contrary to like our future state, where we might like post wait times in a way that we think is the best, the posted wait times right now is really just Disney's best guess of what the actual wait time is going to be at 8 a.m. Like they're doing the best, and that is certainly causally affected by whether or not there's actually magic morning. Because if there was an extra magic morning, there's a whole bunch more people in the park at 8 a.m. compared to if there's not one. So that causally affects that. And then the extra magic morning is also at 9 a.m., like an hour later. It's also going to affect the actual wait time an hour later because same reasons. Yep. So this is a confounder, common cause of our exposure and our outcome. And then one thing that I should have mentioned about these DAGs, these causal diagrams, is that association always flows through these arrows. Like if something's causing something else, there's always a correlation there, always. So like there is definitely a correlation here between extra magic morning and the posted wait time. If you like measured a year of days, like you're going to see a correlation. Same, you're going to see a correlation here. Now, the problem with confounders is that the way correlation flows through this path is going to give us a biased association. I've drawn it actually under the null here. Like, suppose there is no relationship between the posted wait time at 8 a.m. and the actual wait time at 9 a.m. Suppose it makes no difference. Like, who cares? Like, no one's even looking at the thing at 8 a.m. They're just going or they're not going at 9 a.m. If that's null, and then we ran a model without like adjusting or doing something with this extra magic morning variable, we would get a correlation, which would be a wrong correlation. This is the scenario now where a correlation is not causation, because we'd be measuring the correlation that traveled from this path, from posted wait through extra magic morning to actual wait. And that is the wrong correlation that we were like not trying to find, because that's not a causal correlation. So the way we adjust for that then is the way that like we've talked about it for a long time, I suppose. So like this is now we're jumping into R speak here. Rather than like mash a bunch of code, I just thought I'd put like screenshots of what the code would be. And most of you who've worked in R, you'll recognize this. It's just a linear model. Let's say the outcome, the wait minutes actual, averaged over many, many days. So we have like this long data frame with lots and lots of days of actual wait times at 9 a.m. Squiggle, so it like equals just this. So the wait minutes, the posted wait minutes over those same number of days. We will get some correlation from it. Notice we haven't put extra magic morning. If we ran this, we would get some correlation. Like there'd be like a beta, there'd be a coefficient. It would be like, oh yeah, if you increase the posted wait times by 10 minutes, then you're going to increase the actual wait time by like 20 minutes or something like that. They would say that, but it would be wrong because we have a confounder and that correlation is only flowing through this backdoor path, it's called. Okay. But then if we do the other thing, which is better, if we adjust, like this is the thing that everyone's always like told you again in like stats 1 classes, and they're like, we got to control for like these like kind of like loose terms, like let's control for the confounders, like adjust for the confounders or stratify or whatever weird word, that like covariates. We got to do something with the covariates. If you do that, the way you would do that in the simple linear model would be like this. You would just say, okay, yeah. Wait, the actual weight average we're going to regress it and make it be the posted average from an hour before plus the extra magic morning thing that we had to control for. And when we're adjusting for this, we are actually, all this time, everyone in the world has been doing causal inference without actually like explicitly saying that that's what they're doing. The reason you're adjusting for this thing is because when you adjust for it, you block the backdoor path. So like in color codes, kind of like these orange paths in the previous slide, meant there was an open path, but then when you adjust for it, you put it in the model, it closed the path, and now it's gray. So that this correlation now, if we ran this regression, if we've specified this model right, which is something we'll talk about in a minute, then we would get like a 0. Like there'd be no relationship here because there's no arrow left between posted weight and actual weight. We would be getting a 0, which is the correct causal answer. So that's the way, like, with one confounder, this works. But of course, that's not at all how simple the actual problem is. There's lots of confounders in this one, and we've measured all these data points. Okay, so this one's complicated, but we can work through it. We have to deal with many confounders, just like any observational study, whether it's this weird Disney thing or anything else. We want to put on these DAGs all common causes of exposure and outcome, confounders. And we have to adjust for all of them somehow. So we have a common cause here in ticket season. So like peak season, summer, right? Like summer, winter,
Christmas.
like spring break is popular. Sometimes that aren't popular is like February. So like that's important. That's going to cause differences in post wait time because of the volume of people you have there or not. And it's also going to cause the actual wait time because same reason. The average high temperature, people don't like to go when it's like super hot in the afternoon to these things, but they do like to go in the mornings. So if it's going to be a really hot day, you're probably going to have longer posted and actual wait times because people are trying to plan around that and not stay out during the sun. Park closing time, that matters from the day before. Sometimes they do events where they leave the park open until like midnight, so the likelihood that a bunch of people are going to show up at like 7 or 8 a.m. to be in line for this thing is less if they've all been hanging out watching fireworks at midnight. Extra magic morning we just talked about. Okay, so here's all these things, and some of the confounders even cause each other, right? Like it's a complicated thing, but to do the causal inference design properly, you have to walk through an exercise like this. And this, very importantly, is not something typically that the data scientist or statistician can do by themselves. It's just not. Because we tend to be like technical experts, whereas these are like the Disney business savvy expert people. Yes.
So is there a method for identifying these confounders? Okay.
Yeah,
It's not just you come up with whatever.
it's a great question. And the method is not like the answer to what is the method is it's not a technical method. It's a people method. It's a human in the loop method. And this is something that AI, entering now the 2024 buzzwords of the day, like causal AI isn't there yet. Causal, AI and generative AI is very, very good at doing prediction type models. Like you can plug something in and it'll figure out how to fix your code or do something else. But if you ask it kind of like reasoning questions, like what if questions, it sits on top of a corpus of kind of broken causal effects. There's a pretty popular ChatGPT plugin that OpenAI put out called Consensus, and it scoured the whole scientific literature and all the news media and all this kind of stuff. And you can ask it some very basic what if questions. For example, I recently asked it, does hydroxychloroquine, is that an effective treatment of COVID-19? It said, oh yeah, 80% sure, yeah, of course it is. And then we know from trials and others, that's just flat out not true. But it just read all that literature and was like, oh yeah, we see these two things pop up all the time. Hydroxychloroquine, effective treatment of COVID-19, sure, let's go. So it's bad at that. So these days, this is very much a human in the loop process. And so this thing that I'm showing here, this is that C structure platform I was talking about, where you drag these things around. You can almost like a Google Doc, edit them together, and you would do this maybe a data scientist and a couple experts in a room. Almost think about how Google Docs, you see people's little heads hovering in there, moving things around. Some people, traditionally this is even still done in some groups with Post-it groups and things like that. You say, the domain expert will say, what are all the common what are all the things we could think of that we should be measuring that would confound this association between the posted wait time and the actual wait time. In my day job, I do this with medical oncologists all the time. I do not know all the contraindicated medications. If we're studying some particular drug, I don't know all the decision-making nodes that went into their process to decide how to treat a patient, but they do. So if you say, hey, look, I've got this treatment, chemotherapy, and then here's my outcome, it's radiographic progression or something like that. What are all the things that could mess that up and common cause those things? And they would spit out 50 of these things in a minute, and that's what you need to build your model. So it's it's a collaborative thing with people.
So it's domain expertise.
Yeah. Yep. Okay. So yeah, sure. We will adjust them and we want to adjust them somehow. And you might be asking yourself, and this is a good question, you just said that we could just fit the linear model, before when we had this one confounder. So we just said the actual wait minutes, squiggle, the park extra magic morning. Well, then we have this other confounder. Sure, let's throw all these in there too. And does that work? And the answer is yeah. It could work, but the key to most causal inference being right or wrong is in the assumptions that you're willing to live with, and you have to. Like what causal inference does, I think, as a field very well right now, is it helps express and convey those assumptions in a way that everyone can mostly understand them, rather than using vague terms like, we controlled for the covariates, and then we think the effect is this. Rather, we're going to be very specific about, we assumed that this is the set of confounders. You can visually see them and agree or disagree with that DAG. Like a review or two on your paper is going to be like annoying. You could show them the DAG, and you guys could everyone can hash it out together. And then once you decide on those variables, you have to decide how they relate to each other and how they relate to the exposure and the outcome. This model makes some really, really stringent assumptions about how all these things are interrelated. And those assumptions in the linear model space, like we're not going to dive into linear algebra today, but it's like they all have these like linear, the conditional distributions of each of these variables is linearly associated with all the other ones. Like that's what it's saying. And that's super, super restrictive. And in the real world, probably not even close to being true. It's just not. So yes, you could do this. But by virtue of model misspecification now, you're probably going to get the wrong causal answer. Like, yeah, for this one.
Your reasoning is that the relationship may not be linear, even if we control it, right?
That's right. Yep.
Oh,
exactly.
okay.
Exactly. There's a chance that this could get you pretty close. Indeed, we've been using linear models and logistic regressions like this for decades and decades to uncover things like smoking causes lung cancer. Like they weren't doing fancy, like when they were, that stuff didn't require G methods. It didn't require inverse probability. It didn't require much. You mostly could fit the confounders that you knew, like pack years plus age plus sex plus some other like confounders. You're gonna get pretty close. So some things, yeah, but I wouldn't jump to this first usually. Okay, so the G methods that there are many of these, and we're only going to talk about one today. The one you've probably heard of, if you've heard of any of these, would be inverse probability weighting. Sometimes this comes up in conversations with propensity scores, which is basically just a weight. And it's like your probability of being exposed versus not exposed. And you use those weights to create a balanced population, like an artificial pseudo-population of treated and untreated people who are balanced on all the confounders. So it's almost like if you had a randomized controlled trial and you randomly gave half the people A and half the people B, they would be balanced on the confounders by virtue of randomization. What inverse probability weighting does is the same thing, just computationally. It says, oh, if you know what the confounders are and you know what the functional relationship of the confounders to the treatment is, then you can fit some weights and make everybody look balanced on those treatments. That's all I'll say about that one, but we could give, go ahead. We could have whole talks about that, but yeah.
Oh, well, here, you go first.
Well, when you're talking about balance on the confounders between the two groups, what does that mean?
Yeah, sure. So if you did like a table one almost, you could picture where it'd be like the columns would be treatment group A got drug A and treatment group B got drug B, and then in the rows you have like all the confounders where it would be like age, race,
Yep.
sex, like smoking status or something like that. The differences in proportions and values would be negligible.
Okay.
Like which is just what would happen with randomization. If you randomize A and you randomize B, everybody pretty much be balanced on those
Okay.
things. Yeah, good question. Yes.
What's the benefit of doing inverse probability weighting versus doing something like matching? So just you're not getting rid of data? Is there risk of bias? What happens?
Yeah. So so matching is a subset of inverse probability weighting in its own way, because what you do with matching is you set up the propensity score and then you match on the propensity scores.
But do you throw away?
You still end up with it. Well, you can do caliper matching, like you can throw out the edges and like people who don't match. One of the conveniences, I wish Lucy and Malcolm were here because they're like really into this stuff. This is like more my jam. But with the matching, I think if you match in certain ways, you can get different types of causal estimates for the same question. So like supposing that people were like optimally matched, then you get like one type of what's the treatment effect in the group, like rather like a subgroup or a certain kind of patient or participant, compared to like a lot of times with this, and why you can back this into that sort of idea, a lot of times these might just turn out as like the average among like all people in the population. Yeah. That kind of stuff is in this. We talk about that a lot here, actually. Lucy nodded. Cool. Anything else on this one before because that's probably the last I'll say about IPWs. But everyone loves those things. They're cool. Okay. I will not talk about this one at all. G-estimation of a structural nested model. Basically just like layer up these models and then you like estimate something from them and they're super statsy and there's too much like Greek language that we'd have to go through to get to, so we're not going to do it. But this one I love. So the G formula, G-computation, what you do here, and we're going to work through this in detail, is you need to model the joint distribution of observed data to determine potential outcomes under different exposures. So what you want to know, like, what would have happened if I exposed everyone to drug A? What would have happened if I exposed everybody to drug B? These like counterfactual outcomes. Like what would have happened if we'd have done a different thing? To do that, we're going to do some fancy computational stuff. And this joint distribution piece, it's quite honestly not that different than what we talked about in the previous slide, where I said we made these really stringent assumptions about the joint distribution, namely that they were conditionally linearly related to each other, like in this like really strict, simple linear model. The G formula for this joint distribution you're going to see is so much more flexible and gives you so much more control over the assumptions that you're willing to live with. And this is a reference I'll bring up again later, but these G methods, like in general as a class of methodologies, are best described in this chapter from this Fitzmaurice edited book with Jamie Robbins and Miguel Hernan. Brace yourself if you're going to try to read this one. I took a whole class, like all we did is read this chapter for like an entire semester, and we didn't finish it. But it's good. I mean, it's way good. It's like it's the standard for thinking about these things. Okay, so there's 4 steps to this thing as far as I see it. There are some papers out there which are also really good. That do. There's one from Alex Keel which I really like a lot. It's got a little bit more math in it though, and it's something like a what is it called? Like a intuition to a worked example of the G formula, the parametric G formula. And the idea is the same. Like set up some simple rules, like a recipe that you can follow to execute the parametric G formula. Because there's a lot of really mathematical descriptions of the G formula. For example, in that chapter 23 reference I just told you, but there aren't a lot of applied examples out there that people can just like understand quickly and execute in their real life. So step 1 is to draw the time-ordered DAG. We'll do that again in a second. We did that a minute ago. We know what the time-ordered DAG looks like. Just set up the variables that are the confounders and the exposure and the outcome. You time-order them. And you know, with the domain expert, you agree on what that thing is. Then, for every variable which is caused by another variable in the DAG, which is, you can imagine, would be like everything to the right of baseline. So like baseline would be the things you measure first. Nothing's causing them because they happen first. And then everything else is probably going to be some function of those baseline variables. So things that happen at time 1 are going to be some function of things that happen at time 0, and time 2 is a function of both those things, and so on and so forth. You're going to, for every variable in the DAG that is not a baseline variable, create a parametric model, like a logistic regression or a linear regression or something fancier if you want, that predicts each node based on the previously measured nodes. So that's step 2, and we'll see examples of that later. Then, once you have these models specified, so you basically know what the parametric model that you believe is true for more or less every set of arrows in the DAG, you'll draw a large sample with replacement from the baseline variables, like 10,000. There's like rules of thumb around this thing. I don't know, 100,000, it doesn't really matter. You just get more precision as you do more. But if you had like 3 baseline variables, 3 things which nothing caused, which happened first, just start with a data frame that has those 3 variables drawn from with replacement from the original distribution of your data. Like, so if you have 100 people, just like draw 100,000 of those rows. And then you can use the models that you fit in section 2 here, which was let's fit a bunch of models, parametric models for each node. Then you just run all those simulated values through the machinery of the model. So if you want to know what happened in time 1, I don't know, take the random baseline variables and then spit it through that model, that like a logistic regression, let's say, or a linear regression that you set up in step 2, and then you're going to get a bunch of values at time 1, simulated values at time 1, that agree with your model. And then if you want to know what happened at time 2, okay, cool, let's pick up this model, and then now we have simulated data for time 1, the baseline samples, time 1, and then let's get time 2 and just spit it through the model, and then you got time 2. And you just keep turning the crank. There's one exception here. The exposure that you want to intervene upon, like the thing that you want to change, as like the Disney architect or whatever, you know, if you're the person running, like flipping the sign to be 60 minutes instead of 30, don't let the model set that for you. You set it, which represents exactly what would be happening in real life. There'd be all these confounders like causing all these other variables to happen according to some process that you think you've figured out in step 2. But the thing that you're not letting the process generate is what the exposure value is. You said that. So we're going to do that in our data too. We'll say, okay, for half of these 10,000 rows, it's going to be 60 minutes. And for the other half, it's going to be 30 minutes. And then you're basically done because you keep turning the crank on the models that you set up and you end up with the outcome. For 50,000 people that had it set to 60 minutes and 50,000 people that had it set to 30 minutes, and you can compare the average times, let's say, at 9 a.m. on those 2 groups, and that's your causal effect. Like, that's the whole thing. But we'll work through it. Okay? Oh yeah, Monte Carlo, yeah, so the thing in step 3 that I was talking about, drawing a large sample with replacement and then like crunching stuff through the model, that is just a Monte Carlo simulation. So if you're ever reading about these methods and people are saying Monte Carlo all the time, that's what it is. The definition of that, like an approach that just generates a sample of outcomes for random processes. It's often really useful for approximating integrals of all things, which is actually what we're doing. We're actually doing that behind the scenes in this because the conditional distribution of all these things is an integral, and linear algebra is the worst. But you can kind of get around it with a Monte Carlo simulation. And like this super simple example is what's the probability of rolling like 2 ones if you have like 2, you know, like you have 2 die, just throw them. And yeah, we could do this by hand. Like it's 1/6 times 1/6. That's like 1/36, which is about 2.8%. Or we could set up a Monte Carlo process inside of R to do this for us. So I do like, what is this, 1,000,000 draws. 1,000,000 draws, I roll 1 with replacement. I'm gonna get 1 through 6, I roll 2 with replacement, I get 1 through 6. How many times did like roll 1 plus roll 2 equal 2, which only happens when I get snake eyes. And then I divide it by 1,000,000, and aha, I get 2.8%. Great, Monte Carlo to do that probability for us instead of doing the math, which is what he wants to do.
Not a million plus 1. Some would argue for that. Anyway,
What?
I think your procedure is also known as bootstrap, right?
Bootstrap's a little bit. We're actually gonna do the bootstrap later.
Is it different?
Would this be? I don't know. Other opinions on whether it's classified as a bootstrap?
No,
I-
because then
No?
you're treating a finite sample as a population, whereas here you actually have an infinite sample that you're pulling from.
Yes. Yes. Yeah, you could get infinite precision here almost by like letting this run off to infinity. And the bootstrap here is going to have like some bit of error. Like I don't think you get maximum precision. Like to your point. Yeah. Yes. That's a good answer.
Come learn from me in our EATS program.
Nice plug.
Yes.
Can you go back and talk about what this is buying us briefly? About what assumptions we get to
Yeah.
relax? Like, why are we going through all this?
Yeah, good. Let's go.
Okay.
Let's go there next. Actually,
Alright.
yeah, that's good. That's good. So here's the 4 steps again. Good. So step 1 was to draw the DAG. We already did that. We've already discussed it. This is what it is. What we want to do is we want to estimate the causal effect of setting the posted wait time here, our blue and our exposure intervention variable. Let's compare if we decided to set it to 60 minutes or we decided to set it to 30 minutes. Let's find out what the difference here in actual weight would be if we did one of those 2 different things. Okay, so let's pick the parametric models in step 2, and this is going to go right to your question. So remember the alternate world in which we use the linear model kitchen sink. We had this like super simple, like not smart model. We could have made it fancier, but it would still be subject to some pretty rigid constraints, which are that the way the linear model is fit is one big giant like matrix with like stuff, and even if you fit splines and interactions, all kinds of things, all these things are kind of linear related to each other. Now we can actually fit very flexible things at each time point, so that those linear constraints across the time process aren't still true. Does that help answer? Okay, good. Yeah. So like so for the extra magic mornings, that was the thing that happens second in our DAG. So the first thing that happened in our DAG was these 3 things happened at the beginning. We knew the park ticket season, nothing else caused that. We knew what time the park closed the previous night, nothing else caused that. and we knew what the historic high temperature for this time of year usually is. Nothing else is causing that. So those are our 3 baseline variables. So we're going to simulate for time 1, which was the extra magic morning hours, yes, no. We had arrows going from ticket season, park close, and temperature high to extra magic morning. So great, let's fit a logistic regression model to specify whether or not, like what's the probability of an extra magic morning based on the 3 confounding variables that caused it. That's our first model, and we'll just hold it, and we'll call it fit extra magic. And then we have our next one, this is like time 2-ish, I guess. So like a model for the posted minutes. And we're not going to actually use this one because remember I told you we're going to set it, but this can be useful for other reasons if we're just like kind of pedagogically following the process here. We can fit a model for the number of minutes, or the minutes posted, which is its confounding variables that happened previously. Extra magic morning, yes, no, which kind of actually is going to end up coming from there. Park ticket season, was it high peak season, was it not? Park close, time night 4, and the temperature high. So that's the model now for time 2. And then the outcome now is the final one, the actual time that's posted at 9 a.m. You can see we can get arbitrarily fancy with these individual models now. I put a spline in here for the wait minutes posted average that happened at 8 o'clock. So it's like some cubic spline or something like this. And then we have these other confounders in there. So these things can get arbitrarily complex at each building block, at each point in time. You can have a very, very flexible model with assumptions that you might find more appealing to live with instead of just like one big blast of a linear model that all like kind of fits together.
Good question.
Yeah.
When you fit the last model, do you use the actual observed value,
Yeah,
or
great question. Yes, that's a great
magic,
question.
or the predicted one?
Yes, great question. Yes, so when we fit these initial models, we're just going to use the actual data we have in hand.
Oh, okay.
Yeah, and then we get the beta coefficients from this, and then we're going to run the simulated values through, which you'll see momentarily. That's a great question. Okay, so step 3 kind of had 2 parts. We're going to draw the baseline sample, and then we're going to run everything through the models. So the baseline sample is pretty easy to do. We had 3 baseline variables, as we just saw in the previous slide, which was ticket season, time to park close, and then temperature high. So what we're doing here is we are selecting from the 7 Dwarfs train ride from that touring plans package. We're just going to select those 3 variables, and we're going to sample 10,000 of those rows with replacement of all 3. Like we're just retaining that distribution of how those 3 variables fit together in the baseline actual data, and we're going to have 10,000 rows of those. And now you can see where this is going, I hope, because next we're just going to start like taking those baseline 3 values that we have 10,000 rows of and running them through the models that we just fit in the previous step. So we had that fit extra magic morning. So like we have 3 columns right now. We need a 4th column, which is extra magic morning, yes, no. How do we get the yes, no for extra magic morning? Aha, we had a model for that. And it was based on these 3 variables. So let's put it in there. We're going to use augment from the tidy model. Where does augment come from?
They're all the same library type.
Tidy models, whatever. I don't know, but what augment does, it'll add a new column, which is based on a model that we had previously. So this fit extra magic is a model, and then if you say augment, it'll add a new column, and we want it to be the response, a 0, 1, a yes, no.
Broom. Yeah, that's what he said.
Broom, that's the one that is. Is it broom?
I think so. I was wondering if the package that
Yeah.
has the logo with the broom. He's like, Yeah. broom.
Yeah, I didn't say, you answered your own question.
Sweet. So good. Now we have a 4th column.
I think it's broom.
I do think it's broom. So we have 4 columns now. So we have the baseline stuff. We have what happened in time 1, which was the extra magic morning. Yes, no. Now we have we need a 5th column, which is what is the wait minutes that are posted, like the thing that we're going to post and intervene upon at 8 o'clock. And remember, I told you we don't want to use the model to actually generate that. So you can see I'm not feeding the model in here. I'm actually just saying no. Make it be 60 for half of the samples and make it be 30 for the other half of the samples, because that's what we want to do in the actual causal implementation of our strategy. We want to like set it to 60, set it to 30, and then see what the causal effect of that is. What would the causal effect end up being? Well, we have a model for that too. So we had the wait minutes actual, which is now based on all 5 columns of data. So we have all 5 things now in place in our simulated data. And then we just run it through and we get the fitted, predicted actual minutes at 9 a.m., which now that we've adjusted away all of our confounders will be our causal answer. So this is it. So I take that DF outcome was that last thing I fit, where I added that column. I have to do some kind of annoying pivot wider and longer to get this to print pretty, but this is it. So if we set the wait time to be 60 minutes at 8 a.m., after adjusting for all these confounders in very transparent ways with the models that we set up in this Monte Carlo process, then the estimated actual wait time at 9 a.m. would be about 30 minutes. Whereas if we set the posted wait time at 8 a.m. to be 30 minutes instead of 60, then we would get 41-minute actual wait time at 9 a.m. And the difference between those two things, if we post 60, this is what we thought would happen, by the way. If we post 60 minutes instead of 30 minutes, so we say it's longer, less people are going there, and you wait, and in an hour, there's 10 minutes fewer people there. And that's what we thought would happen. And that's from the real data, and I believe this is probably true. So, yeah.
So,
Yes, yeah.
sorry, so I was curious, like, so with this, when you're trying to set the actual intervention in this case, it's just like total balance, it's just like half of the sample is 30 minutes, half is 60. Would there be a situation where you want to have that not be balanced?
I can't think of one, because I mean, honestly, you can arbitrarily increase the number of baseline samples that you generated. Like in that first step, I picked 10,000 just because, I mean, at some point you just hit a wall of computation. Like we could do it with 1 million, and sure, I could do 2/3 and 1/3. But in the end, as I increase that overall size, like it's just my precision. And the 1/3 group is going to be a little bit smaller. So I think the balance is just about precision, probably. One thing that related to that, though, to note, there was nothing magical about me picking 60 and 30. This is something the G formula is really good at. Is you can be very specific about the intervention or treatment regimes that you're proposing. By like say we could have done 45 and 60 and like or whatever.
Can we go back to step 3?
Sure. B. This one. Yeah.
Oh, there are. What's part?
Oh,
A?
actually, it was just it's all. It's all
Oh, I see. So,
yeah.
We simulated the confounders, right? But we still assign the posted wait time. But here, it seems you used, is it random assignment? How was the posted wait time assigned?
Oh yeah, that's a good question. I just took the first 5,000 rows, I gave them 60. I took the bottom 5,000 rows, and I gave them 30. And that works because there's no kind of, what's the word I'm looking for?
No ordering in the data.
There's no ordering, right? Like, I mean, it's all just generated. Like, the distribution doesn't depend on the row number. It's all the same. I don't know if I'm answering that very well. It's not mechanistic. That's the word I was looking for. It's not mechanistic, like according to a row number.
Is this posted wait time a variable originally in the in the bootstrap sample or not?
Oh, it's not. No, the
It's
only
not.
thing in my bootstrap.
Okay.
Oh, good. Yeah, I see where you're going with this. If I did it from the original bootstrap sample, if I put the posted wait time in there, then I might not even have any 60s or 30s. I mean, I hope that I do for 5 other reasons. But like there'd be a bunch of 58s and some 28s and some 29, right? So if I want to actually compare 60 versus 30, then I set them here. Also, if I drew them in the original bootstrap sample, then the distribution of the wait times would still be confounded by these other confounders. What we're doing by simulating this process is we are removing more or less the effect of these intermediate variables by modeling and saying that we understand the process.
Yeah, I guess I need to read the line so I
It's
can
okay.
understand
I mean, yeah,
what
it's
you're
a lot
doing here.
it's a lot to take in, like the first several times seeing this. There was another question, I think. Yeah.
This is trivial, but
It's
where
not
does G
trivial.
come from?
Well, the G, generalized. Generalized.
So how is it generalized?
Yeah.
Well, how is it generalized? He's asking.
Oh, how is it generalized?
Like, what makes it generalized?
Jamie Robbins wrote that original paper in 1986.
So just one guy.
And the answer to that is certainly somewhere in that difficult to read paper. But I would imagine it relates to generalizing the modeling approach from like constricted regressions and frameworks that use like Newton-Raphson and linear algebra and things like that to setting up like just arbitrarily complex time evolving procedures. Maybe. Actually, there might be another answer to this here too, which was I think the slide I was about to get to, which is let's go back to this. Okay, this might be what it generalizes. The G formula is best. I didn't even show you, like I showed you kind of like a simple example. The more complicated examples are extremely useful. So this is from the dreaded chapter 23, which is actually really good. So like here, A is denoting a treatment at time 0, and then a treatment at time 1, and L is a confounder, and then Y is the outcome. So what happens here is, what if you, like, we deal with this in trials, or like medicine a lot. So what if you take like chemotherapy at time 0, and then you like take a break, and then you re-engage in chemotherapy in 60 days or something like that. And in the middle of those, some other stuff could happen, like confounders maybe. And so there are now treatment regimes that could be set up around that strategy, where it's like, take chemotherapy at time 0, take it in 30 days. Don't take chemotherapy time 0, take it in 30 days. Yes, no, no, yes, no, no, right? Like, so there's these time-varying confounders, these so-called treatment regimes, time-varying treatments, I'm sorry. And time-varying confounders can happen too, because the timing, you could even have an L0 back here. So like all the variables are like changing through time. And that is a situation that ordinary regression modeling cannot fix. It cannot do it. Because what happens is, like basically if you adjust on this thing, then you open a new backdoor path, but you have to, like, so maybe you don't adjust for it, but if you don't adjust for it, then you have a biased path still. Like, regression can't fix this problem. So the thing that I set up way in like slide 2, I was like, yeah, kitchen sink linear model, go for it. That won't work here. The only thing that will work is G-methods to like get rid of the biasing effects and estimate these dynamic treatment regimes. Like that's the only way to do it. So maybe that's why it's generalized. I kind of guessed, and hopefully Jamie doesn't watch this talk and then send me an email, which I very much doubt. Yeah.
So let's say someone was taking just a linear approach, or a linear regression approach.
To this?
Yes.
Yeah.
What signs would there be that it's the wrong approach?
There wouldn't be any. What would happen is they would not have been like this happens in papers all the time. So I remember reading a paper like I don't know, a while back, and it was like more cycles of chemotherapy led to longer survival.
Okay.
I mean, leaving the obvious note aside that like you have to live longer to receive more cycles of chemotherapy. Like leaving that aside, actually, there are lots of different biasing things that could be going on, where they might have adjusted for things that happened post-baseline, and I'm certain that they did. But it's kind of like masked by the complexity of the general like paper and methods that they're describing. Like, well, we had these patients, and then some stayed on study, and there's like an elaborate consort diagram, and and then you go, oh, and then we ran a logistic regression and something, and here's proportions, and it looks convincing, and these things land in good journals, but it's hard. Like, and I just don't. These models today, I don't think like people aren't drawing DAGs. I guess to answer your question, like without the DAG to like make everyone stare at it and go, wait, there's a path of association that's biasing, and you need to tell me how you close that path. Without that happening, I don't think that it's obvious to anyone just reading paragraphs of text. I think these are the key.
What proportion of papers do you read where you see this stuff?
Oh, I mean,
50% more.
I mean, the ones with stuff that happens over time, like many. Like, they're hard.
Yeah.
Dealing with time-dependent confounding is really, really tricky. And like, honestly, the computational tools and accessible computational tools haven't been out there. So I don't fault anyone for like not doing it like this way.
Is this a plug for your software?
What's that?
Is this a plug for your software?
It's not yet. It could be. Yeah. I just think it's hard, and this is an emergent. Like, this is the edge of the field. Just because like a lot of the papers didn't do it exactly this way, I don't think like the entire scientific body of literature is busted.
No, absolutely.
In this figure you're showing A are exposures, right?
Yeah.
What is L?
A confounder. Yeah.
A confounder. And what is U?
An unmeasured confounder, actually.
I see.
Yeah, so what's interesting
Okay.
is like if you have to condition on L to get rid of the confounding effect of L on A1. So you have to condition on it. But there's a rule of DAGs where this is called L as a collider. Two arrows collide there. When you condition on a collider, you open that path now, and now A0 is confounded through this path. So it's like you're damned if you do, you're damned if you don't with L. You have to adjust for it, but you can't adjust for it. And that's why standard methods don't work.
So what if here for all the exposure that's A, we use random assignment? Does this solve the problem?
No, great question. This effectively is drawn under random assignment because nothing is causing A0.
Oh, okay. So even both A0 and A1 are randomly assigned.
Great.
We
That
still
would work.
cannot get.
Ooh, that would work. That would work. Because then you would have no arrow from L1 to A1. There'd be no arrows into A1 because it'd be random at that point.
Ah, I see. So you're saying that usually in reality, we can usually randomly assign exposure at A0. But usually when we go to A1, that's in the future, it's not really random, right?
Yeah, because
Oh.
it's a treatment pattern, right?
Yes.
You have to follow a particular regimen.
Yes.
And in oncology, it's like very common. You have lines of therapy that you're examining.
Perfect. Yep. That is it.
So one of the things that is standing out to me is that you have to have like all these models kind of building on each other before you can run the simulation, and each of those will have something like confidence intervals or something along those lines. With this, is there an equivalent for like your actual relationship of interest at the end?
I think you're getting at how do we get confidence intervals out of this?
Yeah.
Yeah, good. Yeah, and that was this slide that I skipped.
Perfect.
Great question. And this is I think one of the reasons I was saying like not a lot of people are doing this because until very recently you wouldn't want to like I did some of these in grad school. I mean like back in I don't know, this is more than 10 years ago now. But I remember when I used to do G-computation in grad school, I'd have to put my computer, like, because it would be burning up all night, I'd put it on the side like this, and it would go, bzzz, and then my wife, she'd always be like, she'd call it cooking code. She'd be like, are you cooking code tonight? And I'm like, yeah, like I'm cooking meth or something. But like, anyway, now this is possible, but this used to be really, really hard, like for computational reasons. Basically, that whole thing that I just showed you, like you nest the whole thing in a bootstrap, like the baseline samples, the whole thing. So you got that process that I just showed, which is like kind of non-trivial in and of itself because you're fitting a lot of models, you're doing some other things. Do that like 100,000 times, and that's how you get confidence intervals out of it. If you want to know how to do that, that's why I took a screenshot of this. So I just finished this chapter maybe like 2 weeks ago, and the example in this chapter is the example we just walked through, but the way I present it in the chapter wraps it all in the bootstrap. So if you want to get confidence intervals, it's all there. That might have been it. Oh yeah, that was it. Yeah.
What
So
did you-
yeah, go ahead. Yeah, I mean, I talk fast, like I don't know, we can hang out, but yeah.
Oh, nothing. I was just curious. What happens when you flip the laptop? What does it do?
Because the processor, I mean, maybe it's less true on these M1s now, or this M2, but like the processor on the old Macs, it would get like really, it would like get scorching hot here, and I was worried I'd burn my house down, because and like the fan would be going, and it was really hot.
That happened
yeah.
when you do bootstrap.
Oh yeah.
Oh, okay.
Definitely. Yeah.
Strap an ice pack to it.
Are you using, so like, in terms of the frameworks or packages that you're using when you're doing this kind of bootstrap simulations, are you using like FUR or PRMS or like?
I'm using the boot pack. I mean, I just use the simple boot package,
Okay.
which I don't know. I have no idea if it's the most computationally efficient or not. I mean, fortunately for me, it's not like I run these models like 100 times a day. Like, like 99% of all the work that goes into fitting one of these things is getting people to agree on the DAG, like identifying what the parametric models are going to be, and like all that stuff. And then you run it once, and then maybe you have to run it 3 or 4 more times to like troubleshoot some goofy bugs that you injected into. But like, I'm doing a lot. But you're right. Like Bootstrap should be like embarrassingly parallel. Like, I mean, you should be able to GPU it, like do all kinds of things for large data. But I don't run into those problems myself.
That's good, yeah.
Yeah, go ahead, Rebecca.
So I was going to ask a question that you just kind of started to address. So it seems to me like that first setup of the assumptions about how things are related is the hardest part, and you know, identifying them, confounders, plenty hard. How 4 or 5 different models, like what is the hardest? Sorry, sitting down with the subject matter experts and like talking then about the relationships between patient characteristics and drugs that they're on and how they will respond to them. Like that sounds incredibly hard to do, and that's kind of important. So what do you find to be the hardest part of this?
I mean, I think the biggest barrier to like activation barrier is the DAG, like drawing the DAG and making sure that everybody gets all these things on paper. Once you have the DAG,
do you feel like your DAGs are good? Like, how do you know that?
Whether or not they're good, at least they're clear. And
Okay.
I think there's a pretty big thing to be said about that, because if you've encapsulated the DAG and if you publish the DAG, then if people have something to complain about
Okay.
with your, I mean, fine, like good. That's the scientific discourse, right? Like, let's do it. So I think that's a huge plus, whether or not they're right. And I think over time, like we'll bend towards like actual surety. The more people look at these, the more people draw them. The modeling part of it, like the actual model specification, the subject matter experts I think have less, like they don't. I don't want to say they don't care, but like whatever. That's like more of a data science concern. There's some packages out there that do this. Like there's the G formula package from Miguel Hernan's lab that has some pretty reasonable defaults. Like it'll fit like splines and some interaction for almost everything. Like just out of the box, it's like, oh, we're just going to fit very flexible parametric models given a DAG.
Yeah.
And that's usually.
Yeah, no, I was even thinking
Yeah.
like, I mean, I've been to Disneyland once, thank you very much, but even so, like, what was supposed to be a simple example, I was still like sitting at and being like, wait, does it have no input? Even the
Right.
simple
Yes.
aspects of it still seemed complex to me, so when you're sitting down with a disease course you don't understand,
Yep.
I feel like that's just very hard to, even figure out what you're splitting it up into.
Yeah, no doubt. And in general, the process for that, it's wise to start with the saturated DAG, so like arrows to everything, from everything, because the impact of an incorrect assumption about an arrow which is not there, which should be there, is far greater than having an arrow there which didn't need to be there. So like it's good to like start with the full DAG and then peel back with the domain experts in there. Like if they really don't think this other thing caused the other thing, then good, let's take it out. But otherwise, let's leave it. Okay, yeah, put links to the chapter 23, with all the G methods you don't, and then, so that's like theoretical, mostly, almost entirely, but it's, if you like math, that's your thing. This one is the book that Lucy D'Agostino-Gallon and Malcolm Barrett and I've been working on for a long time now. It's fully, we're fortunate that CRC Press let us put it on this website, so like, as we update it, if this website updates, it's more than half written. We're pretty close. And then, so all the DAGs I put in here, like the visuals for my thing, were from the C-Structure platform, which I'm working on. But if you want to do DAGs only in R, and there are good use cases when you'd want this to be true, like if you want your code and your DAG and everything all version controlled in the same like place, and sometimes there are things that talk to each other like this. This is Malcolm Barrett's package. It's called GGDAG, and that's what the help files for on it. So it'll make nice DAGs like in R with the ggplot syntax for you, if that's what you want to do. And that is it.
Can we possibly move back to the step 3B part?
Step
I really
three-
want to
yeah,
see what you
yeah,
did
let's
there.
okay, let's look at it.
Thank you.
Okay, so while Jerry's thinking,
Yep.
so can you,